equal. Now, in this case, what's going to happen that you have, uh, and I'm going to construct that table again. Okay, so you're going to have your initial moles and your final moles. So let's say this is our table, and initially, right at the beginning, ठीक है, अहमद ये आप गौर से सुनना, ठीक है, right at the beginning, initially, ठीक है, you had a container and you added 0.8 moles of N2O4, right? And there was nothing, there was no NO2. So eventually, what would happen? A reaction would start. They would, but the N2O4 would start reacting. ठीक है, the amount of N2O4 would start decreasing because you've got N2O4, it would start decomposing, the amount of NO2 would start increasing, the amount of N2O4 would start decreasing. Ahmed, is this clear?
Yes, sir.
So, and eventually when NO2 is formed, a reverse reaction would also start and then the amount would stop changing. Okay, if 10 molecules of NO2 are formed and 10 molecules are formed back again, so the amount becomes constant. And that is the point when equilibrium is reached. So anyways, after several days, the reaction going forward and backward and forward and backward, eventually an equilibrium is reached. And when they opened the container at equilibrium, they found out that there was zero point 0.3 moles of NO2 that was present. So what does that mean? It means that at the start you didn't have any NO2, but now you have 0. Now you have zero point 0.3 moles of NO2. So that indicates that zero point 0.3 moles of NO2 have been produced. They got produced. A reaction must have occurred. There would have been more forward reaction and zero point 0.3 moles of NO2 were produced. Ahmed, is this clear?
Yes.
So if zero point 0.3 moles of NO2 are produced, it's 2:1. That means, according to the ratio, if 2 are produced, 1 and 2O4 must have reacted. So if zero point 0.3 is produced, then on this side, how much would have reacted? 0.15 moles must have. They must have taken part in the reaction, right? So out of the zero point 0.8 that you initially added, 0.15 must have reacted. 0.15 are gone. So if you subtract, because 0.15 have taken part in the reaction, so that because over here you 0.3 moles of extra are getting produced. So 0.15 are gone, they've reacted. So out of the 0.8, 0.15 are gone. So what are you left with? You're left with 0.65 moles at equilibrium. Is this clear? Mariam, is this clear? Ahmed, is this clear? Zari, is this clear?
Like, why did we remove 0.15 then?
क्योंकि 0.15 moles reacted. ये तो clear है ना, 0.15 moles reacted.
And yes,
तो खत्म हो गया ना 0.15. तो 0. अच्छा, सॉरी, 0.8 से ना अहमद, 0.8 से स्टार्ट में कंटेनर के अंदर 0.8 ऐड किया था आपने ना इनिशियली, राइट? कंटेनर था, यू एडेड 0.8, तो 0.15 मोल्स हैव रिएक्टेड, तो खत्म हो गए, दे गॉन. तो 0.8 में से 0.15 दैट्स गॉन. सो व्हाट आर यू लेफ्ट विद? 0.65 सब्ट्रैक्ट कर दो. क्लियर है?
yes,
Achha, so I'm just going to, just to ensure okay, we get this, I'm just going to make random equations. I'm going to make these random tables and keep on repeating this. Okay, so let's take another reaction. I'm just going to, I can't think of reactions. I'll just take A and B. So A is reacting with 3B to produce 2 molecules of C. Okay, so let's say there's this reaction. A reacts with B to produce C. And I'm going to make a table. And the table will have so the table is going to have your Okay, so here's our table. So here's my table, and initially in the container now, so I'm going to make this more difficult. Initially in my container, I have I took a container and I started adding A, B, and C in that container. So I had zero point 0.6 moles of A, and I had zero point 0.4 moles of B, and I had zero point 0.9 moles of C in my container. Okay, so I had these many moles in my container, and so I mixed them, and the reaction started. Okay, so A and B, they started reacting with each other to form C, and C that was present over here, it started reacting and eventually started forming A and B, and eventually forward and backward reaction started, and at some point they reached equilibrium. So the rate of forward became equal to the rate of backward, and that is when the equilibrium was reached. And when the container was opened at equilibrium, you found out that there were zero point 0.7 moles of B present. That's the information that's given in the question. So you opened the container and you had exactly zero point 0.7 moles of B that were present in the container. So what does that mean? That means, okay, these were the moles that you initially added. And Emma, is this clear? Okay, initially you added these all of these and you mixed them up. Okay.
जी.
Now all of a sudden when you opened the container you found okay, the quantity of B has increased. Like you added zero point 0.4, now you have zero point 0.7. So that means how many moles got produced? There's an extra zero point 0.3 moles present. So that means 0.3 moles extra have been produced during this back and forth. There's an extra zero point 0.3 moles that have been produced. I think I'm just going to write point plus zero point 0.3 over here. So that means an extra zero point 0.3 moles have been produced. So where did they come from? There must have been C that would have that would have reacted and that would have formed this B and this A as well. So these moles are getting produced. Is this clear? Zari, is this clear? Mariam, is this clear?
Yes.
So zero point 0.3 moles are getting produced. So how many moles of C must have reacted to produce these many moles of B? The ratio is 3:2. So if you have 0. 0.3 moles getting produced, three, if you want to produce three, two of C must have reacted. So 0. 0.3 getting produced, that means 0.2 moles, according to the ratio, 0.2 moles over here must have reacted. So if they have reacted, then that means they're gone. Okay, so there would be 0.2 moles that are missing. And if three B's are produced, one A must have been produced as well. So if there's 0.3 moles getting produced, then the amount of A that's going to be produced according to the ratio, it's going to be 0.1 moles. They would be produced as well. So you're going to get an extra 0.1 moles of A as well in the reaction. Okay, is this clear?
Yes.
So now, Emma, are you clear?
Yes, sir.
So final moles. Initially you added 0.9, 0.2 are gone. So that means you're left with 0.7 moles. Over here, initially you added 0.6. There's an extra 0.1 that's forming. So that's now 0.7 moles. Okay, so you get an extra 0.7 moles of A. Uh, let's do another one. Okay, I'm just going to take A and B. So let's say I have a reaction. There's 2A that's reacting, and there's an equilibrium reaction that's happening, and you're getting uh, B plus C. So that's my reaction. Again, make a table, and So here's my table. Let me just move it slightly. Here's my table. So my initial moles that I added in the container. I added right at the beginning. I added 0.5 moles of each substance. I just mixed them up. TK cannot write. I'm not going to write it here. TK writing it in the table. So, anyways, I added 0.5 moles of B and I added 0.5 moles of C as well. And then at equilibrium, I figured out that once a lot of forward and backward reaction has happened and the rate of forward became equal to the backward reaction, and I opened the container after several days, I found out that there was 0.6 moles of C in my container. So what information do I get from this? That initially there was 0.5 moles, and after several days there's 0.6 moles. So that means there's 1.1 moles of extra C that's getting produced. So you're getting 0.1 moles of C that are getting produced. Is this clear? ठीक है, is this clear? Mariam, is this clear?
Yes, sir.
Yes.
So now according to this, if 0.1 moles are getting produced, that means there's a forward reaction that's happening. 0.1 moles are getting produced. So it's 1:1. If 1C is produced, 1B would also get produced. So if 0.1 moles are getting produced, then according to the ratio, 0.1 mole of B must have been produced as well. And if 1B is produced, 2A must react. So 0.1 are getting produced, so double that amount must have reacted. So 0.2 they must have taken part in the reaction. And so according to that, 0.2 are gone. And there's an extra 0.1 getting produced. This was already 0.1 getting produced. So how many moles do you have in equilibrium? It's going to be 0.6 for this. And it's going to be 0.3 moles for this. TK, is this clear?
Yes.
So let's try and do more questions related to this, more past paper questions. TK, for example, I have this reaction. And we're going to do the same thing. So they've given me an equilibrium reaction, and not this one, this one. So they've given me an equilibrium reaction, and they've told me the initial situation and what does the equilibrium contain at the end. So I'm going to do the working over here. The reaction is 2NO2, right? It's an equilibrium with 2NO. It's an equilibrium with 2NO plus O2. Okay, that's what the reaction is. I'm going to construct the table quickly. So I'm going to construct the table, and it's just 1 second, buddy. So that's just. So I have my table over here. The first row is the initial moles. So how many moles did he add into the container? He added, like if you read the question, that 4 moles of nitrogen dioxide were put into a 1 dm cube container. So 4 moles of nitrogen dioxide were put into a container. So initially the container only had NO2, nothing else. So there was nothing else. There was no NO and there was no O2 as well. So they were not present. And then what he did, he said that the container was heated to a constant temperature and equilibrium was reached. So the equilibrium mixture contained 0.8 moles of oxygen. So once equilibrium had reached, your container had zero point 0.8 moles of O2. At the beginning, the container had nothing. There was no O2. But now it has zero point 0.8 moles of O2. So that clearly means that O2 got produced in the reaction. How many moles? 0.8 moles of O2 were produced during the reaction. So you have an extra zero point 0.8 moles. Is this clear?
Yes.
TK, Emil, are you getting this?
Yes, sir.
Achha, so initially 4 moles, he added 4 moles, and when equilibrium was reached, he found there was zero point 0.8 moles of O2. So where did that zero point 0.8 moles come from? Because initially there was no O2 added. So that obviously means that there was a reaction going on, a forward reaction, and zero point 0.8 moles got produced. Now what's the ratio? Okay, if one O2 is produced, 2 NO are going to be produced along with it. So if 0.8 got produced, then according to the ratio, it's 1:2. So 0.8 ratio, it's going to be 1.6. So 1.6 of NO must have been produced as well. So that means there's going to be an extra 1.6 moles in the container. And if zero point 0.8 moles is produced, how many moles of NO2 must have reacted? It's again 1 O2 is produced when 2 NO2 react. So 0.8 are getting produced. That means 1.6 over here must have reacted. So if they are reacted, they're gone. So out of the 4 moles, 1.6 is gone. So what are you left with? You're left with 2.4. And what are the moles of NO? That's initially you had no NO, and now 1.6 got produced. So that means you have exactly 1.6 moles. These are your equilibrium moles. Is this clear? Is this?
Yes.
So, Kosa, is this clear?
Yes, sir, it is.
I said now you're being asked to find the value of Kc as well. So remember, I told you the Kc, the expression for Kc is going to be it's a ratio of the product concentration divided by reactant concentration. So you're going to find the find Kc. Kc is going to be product. The products are NO concentration and O2 concentration divided by the reactant concentration, which in this case is NO2. And I told you the coefficient becomes the power. So if it's 2NO2, it's going to be NO2 squared. If it's 2NO, it's going to be NO squared. So I'm just going to plug in these values, the ones that I've found over here, and I'm going to plug in these values over here. And remember, these are moles. In the Kc expression, you always use concentration. What is concentration? Concentration is moles divided by the volume. So the volume of the container is 1 dm cube. So it's 2.4 mole per dm cube. So there's no point in dividing by 1. You get the same value. But ensure that you're using concentration. So I'm going to plug in the values, and somebody should keep the calculator open. It's going to be product. It's going to be NO, which is 1.6 squared. I said you don't have to. They're just looking for the expression multiplied by 0.8, and you're going to divide the whole thing by 2.4 squared. So the correct answer to this one is going to be, I think, it's going to be D. So that's your question. Now let's move. So we're done with this question. Let's move to another question. And another question where we have to do the same thing. Not this one. I said this one. Again, in this question, they gave you, I'm just going to focus on this. They gave you X and Y. There's X reacting to form 2Y. Okay, so let's make the table. So I have my initial moles. How many moles did he put in the container? A solution X has initial concentration of 0.5 mole per dm cube. So initially per dm cube, there's 0.5 moles in the container. and there is no y. So y is completely absent. So there is no y. So 0.5 mole per dm cube of x was put in a container. When equilibrium was reached, it was the concentration of x had fallen to 0.25. So once there was forward and backward reaction happening and the reaction was going on at equilibrium, you found out that the concentration had dropped to 0.25 moles. So what happened here? Initially you had more x and now you have less x. So that means 0.25 moles are gone, which means that 0.2425 moles have taken part in the reaction. They have reacted, right? They're gone, they've reacted. Okay, is this clear? Anna, is this clear?
Yes.
Achha, so 0.25 are gone because initially you had 0.5, now you have 0.25. So that means there's 0.25 missing. Where did that go? They reacted and they must have formed y. So according to the ratio, it's 1:2. So if 0.25 react, on the other side, how many y would be produced? 0.5 of y according to the ratio 1:2, it's going to be produced. 0.5 moles would be produced. So 0.25 were missing. So over here, 0.5 moles got produced. So how many moles do you have at equilibrium? Like initially you had no moles of y, but now 0.5 got produced. So how many moles do you have? You have exactly 0.5 moles per dm cube. Uh, so I found my equilibrium moles, and he's asking you to calculate the value of Kc. What is going to be the expression for Kc? Kc over here would be product concentration y divided by the reactant concentration, which is x, and the coefficient becomes the power, so it's 2y, so it's going to be squared. So I'm going to plug in the equilibrium concentrations. It's going to be 0.5. So put in 0.5 over here. That's going to be squared and divide by the x concentration, which is going to be 0.25. If you solve for this, I think you're going to get 1.
Yes, you get one.
So you're going to get 1. So your Kc value is going to be 1. And he was also looking for the graph as well. So the graph is that the concentration of x starts at 0.5 and it eventually drops to 0.25. So the concentration of x is going to look like this. It starts at 0.5 and it drops to 0.25. And the concentration of y starts at 0 and it increases to 0.5. So the graph would probably be this one. It's going to be C. That y starts at 0 and goes up till the 0.5 mark. And the concentration of x starts at 0.5 and it decreases to the 0.25 mark. So the graph is probably going to look like this, according to the information that's given. And the value of Kc is going to be 1. They were looking for the value of Kc. So it's going to be 1. Is this clear?
Yep. Yes.
So let's do this one now. So again, you have the same. What are the initial concentrations? Again, it's a 1 dn cube container. So, I mean, there's no point dividing by 1. You're going to get the same value. So initially he added 1 mole of silver nitrate. Silver nitrate is silver ions. It has Ag plus 1 ions. So this is my initial. I'm not going to draw the table now. So I've got 1 mole of Ag and I've got 1 mole of FeSO4. FeSO4 is Fe2 plus. So those are my initial moles. There is no silver and there is no iron 3 plus. Okay, they're not there. And then he says that equilibrium was established. So there's going to be a forward reaction, backward reaction. Eventually, the reactions continue, and after some time, there's going to be equilibrium. And he now says that at equilibrium, there's 0.44 moles of Ag plus 1. So Ag plus 1 moles are now 0.44. So you started off with 1 mole, and now you have 0.44 moles. What does that mean? That means that 0.56 moles are gone. 0.56 moles are missing. So that means 0.56 moles must have reacted. TK, is this clear? Emma, is this clear?
Yes.
So you started off with 1 mole at equilibrium, and eventually you're left with just 0.44 according to the information that's provided over here. So 0.56 must have reacted. So in what ratio do they react? 1 reacts with 1. So if 0.56 of Ag plus 1 is reacting, then 0.56 of Fe2 plus must also have reacted. So that means 0.56 of these moles are also gone. And you're left with 0.44 moles of Fe2 plus. And 1 reacts with 1 to produce one of this and one of this. So if 0.56 react with 0.56, then they're going to produce, according to the ratio, it's 1:1. So they're going to produce 0.56 of this and 0.56 of this. They are going to be produced. So there's going to be an extra 0.56 moles of Ag as well as Fe3 plus. So Ag moles would be 0.56 and Fe3 plus moles would also be 0.56. So those are your equilibrium moles now. Okay, is this clear to everyone?
Yes, sir.
And you're being asked to find the value of Kc. So Kc would be product concentration. So it's going to be the concentration of Ag solid into the concentration of Fe3 plus aqueous divided by the concentration of, and concentration would be simple. The container has a volume of 1 dm cube, so it's all going to be moles divided by volume is concentration. So all of them would come out to be exactly the same. As anyways, divided by the reactants, which are Ag plus, and you have Fe2 plus. Now, tell me what is wrong with this expression, the one that I've written. I mean, Kc is always product concentration divided by reactant concentration. These are my products. These over here are my reactants. But there was can anyone point out what's wrong with this expression? Okay, I mean the expression is fine except for one thing, which is that whenever you have a solid, solids, the term concentration doesn't really apply to solids. I just told you when we were doing this. I told you that solids concentration is always taken as a constant. It's always taken as one. You don't write solids in the expression because their concentration is not going to change. Why? Because I told you concentration is about spacing, like how close together or how far apart particles are. In solids, the concentration is they're always tightly packed. So you never ever write solids in the expression. Never ever to write. You don't write solids in the expression. That's it, because their concentration is always a constant. So we're going to calculate Kc, but without the Ag solid. So it's going to be Fe3 plus concentration, which is 0.56, and it's going to be divided by the reactant concentrations, which are 0.44 multiplied by 0.44. What do we get? Has anyone calculated this?
2.89.
Okay, so we're going to get 2.89, but be very careful that in the expression of Kc, products over reactants, you always and this is something that was done as well when we were doing this somewhere over here, where I explained that when it comes to concentration, the term concentration is only used for solutions or for gases only. For solids, because they're always tightly packed, concentration is a concept that it talks about spacing of the particles. So their concentration is always taken as a constant. It's always taken as one. And I also told you that if water is in large excess, or if it's aqueous, anything that's in large excess, its concentration would also be taken as one because it's not going to change. So remember that when you calculate Kc. Let's do. So these are all about units. Let's do this one, I think. Yes. Let's try and do this one. You've got N2 and you've got 3H2, and they are in equilibrium with 2NH3. So initial, and you have your equilibrium. So what are your initial moles? 1 mole of nitrogen and 3 moles of hydrogen and 1.98 moles of ammonia. So there's 1 mole. This is 3 moles, and ammonia is 1.98 moles. They are mixed in a container, and they're all going to react with each other. And when they start reacting, it was found that once equilibrium was reached, it was found that 1.64 moles of nitrogen were present. So at equilibrium, you've got 1.64 moles of N2 in the equilibrium mixture. What does that mean? That you started off with 1, and now you have 0.64. So that means 0.64 extra have been produced. So that means, where did they come from? There must have been backward reaction going on. There must have been more backward reaction going on, which resulted in an extra 0.64 getting produced. Is that clear?
Yes.
So if 0.64, it's 1:2. If 1 N2 is produced, 3H2 must have produced along with that. So it's 1:3. So if 0.64 are produced, what's 0.64 times 3? That's going to be 1.92, right?
Yes.
So N2 can't be produced alone. There's going to be 1.92 extra. I'll send it, TK Alicia. So there's going to be 1.92 moles of H2 also getting produced, right? So that means there's an extra 1.92 moles of H2 now. So at equilibrium, you now have that you already had 3 moles. Now there's an extra 1.92, so you have 4.92 moles, right? So what happens to NH3? The NH3 is the one that must have reacted to produce this. So 1N2 is produced when 2 NH3 react. So it's 1:2. So 0.64 must have been produced. If double that amount, what do you get? It's going to be 1.28, right? Okay, 1N2, according to the ratio, 1N2 is produced when 2 NH3 react. So 0.64 of N2 must have been produced if 1.28 of NH3 must have reacted. So reacted means they're gone. So you subtract minus 1.28. What do you get? What's 1.98? It's 0.7 or what? 0.7?
Yes.
So you're getting 0.7 moles. So you found your equilibrium moles now. TK, you found them. Convert that into concentration. That should be easy because I think they gave you a 1 dm cube container or not. So they should have, well, it's not given here, but usually in questions, this should be given. I said, but anyways, you just have to find the expression for KC. It's going to be product concentration. It's going to be NH3 concentration, which is going to be squared. So it's 0.7 squared. It's probably the first one. So NH3 concentration squared divided by your reactants, which are N2 concentration. That's 1.64. And this one would be 4.92 cubed because H2 is cubed. So products over reactants. So it's going to be A. Is that clear?
Yes.
Yes.
So another one, Teague, it's a similar question. It's exactly the same one. So N2 plus 3H2 and you got 2NH3. So initial, right at the beginning, 2 moles and 6 moles and 2.4 moles. And you have 2.4 moles. They're mixed together. Now, what happens after that? What happens after that is that, and it's now he told you it's a 1 dm cube container. In the previous question, they should have told you that what is the volume, because you can't find concentration without the volume. It was found that at equilibrium there was 2.32 moles of nitrogen. So once the reaction started and equilibrium was reached, he found out that there was 2.32 moles of N2, okay, which is given over here. So you started off, initially you added 2 moles into the container, now you've got 2.32. So that means there's an extra 0.32 that got produced. And where did that come from? Because initially must have reacted and must have produced more N2. So 0.32 got produced. So if 1 N2 is produced, 3 H2 are also produced. So 0.32 are produced. Then along with it, there's going to be according to the ratio, that's going to be 0.96. Right? Is this clear? Do you guess this clear?
Yes.
So there's an extra 0.96 that's getting produced. So you have 6.96 moles. Like you already had 6 moles. Now there's an extra 0.96 getting produced. So you have 6.96 moles. And to produce 1 and 2 NH3 must react. So to produce 0.32, according to the ratio, 0.64 must have reacted. So 0.64 are going to be gone. And what happens if you subtract 0.64 from 2.4? That's probably going to be 1.76. Those are your equilibrium moles. Is this clear?
Yes.
So it's going to be 1.76. And the next thing is you just have to write the expression NH3 concentration squared. So it's going to be 1.76 squared. So any one of these two. Divide by your reactants, which are 2.32. So that's fine. And 6.96. So it's going to be A again. So that's going to be your answer to this one, to this particular question. So remember how to do this. It could get confusing, but practice. You can practice a lot. You can make sure if the amount at equilibrium increases on one side, that means there's more of these things getting produced, and the other side is reacting. So that means that quantity on the other side is decreasing. So I'll send the worksheet. TK will do some more questions on this because that's the only difficult part in this entire topic. Achha, is this clear so far? These questions.
Yes.
So let's continue next week then. Okay, I'll send you the worksheet in the group. This particular worksheet. So okay then. Take care.
Okay, thank you. Allah.
Allah Hafiz.
Allah Hafiz.